Voltage and electric current. Moving two positive charges together requires us to apply a force, since like charges repel each other. So two positive charges, and this represents the force. This results in work being done on the system since a force is applied over a distance. The work increases the electric potential energy of the system. Just like applying a force to raise an object above the floor adds potential energy to that system, gravitational potential energy. A measure of the amount of increased electric potential energy per unit charge is voltage. A 1.5 volt battery adds 1.5 joules of energy to every coulomb of charge that passes through it. Batteries convert chemical potential energy into electric potential energy. Both of these batteries have the same voltage, 1.5 volts, so each electron that leaves the battery has the same energy. The larger battery, that is the AA battery, has more chemicals, so it lasts longer than the AAA battery. When electrical engineers need to design circuits to bring electricity to users in industry, businesses, homes, manufacturing, laboratories, etc., they use diagrams with symbols. These diagrams are then used to build out the circuits. This is a symbol for a cell or battery. More symbols will be shown in the next unit, circuits and practical energy. So the long vertical bar here, that's the high voltage terminal, and the shorter one is the low voltage terminal. And on a cell or battery, there's your high voltage, there's your low voltage. Electrical energy imparted by the battery is carried by moving charges and is used by various circuit elements and electrical equipment, such as light bulbs, motors, computers, radios, kitchen appliances, etc. For example, a light bulb converts the electrical energy in the charges into heat and light energy. After the charges pass through the light bulb, they have less energy than they had before the light bulb. Since the electrical energy decreases, the voltage also decreases. This is called the voltage across the light bulb decreases, or there's a voltage drop across the light bulb. Electric current is the rate of flow of electric charge. The letter I is the symbol for current. So I is Q over T. Q is the amount of charge, and T is the time it takes to flow past a location. That can also be written as delta Q over delta T. Current has units of amperes, A, often called amps. Since charge is measured in coulombs and time is measured in seconds, 1 amp is 1 coulomb per second. A good analogy to help understand voltage and electric current is to consider water flow. The flow of water in a pipe is similar to the flow of electrons in a wire. When water flows through a pipe, the amount of water entering and then leaving a length of the pipe is the same. When electrons pass through a wire segment, the amount of electrons entering and then leaving the wire segment is the same. Water flow depends on the pressure exerted on it by a pump or gravity. The greater the pressure, the greater the water flow. Electric current depends on the pressure exerted by the voltage. The greater the voltage, the greater the current. An electric circuit is an external path that charges can follow between two battery terminals. For charge to flow, the path must be unbroken. So it's not like a water pipe, right? Because if this were a water pipe and you broke it, the water would still flow. However, for charge to flow, we must have a complete path from one end of the battery to the other. An example of a conductor used to form a circuit is copper wire. Continuing the water analogy, one can think of a wire as a pipe for charge to move through. A pump pushes water through a pipe. For electricity, a battery pushes current through a circuit. Charges do not move through the circuit unless there is an applied voltage. Batteries have a potential difference between their terminals, and by definition, conventional current moves from the positive terminal to the negative terminal. Actually, electrons, which have a negative charge, are moving in the opposite direction, but the effect is the same. The convention was established before the discovery of the electron. And over here is a nice video to click on for a nice explanation of current. All materials resist the flow of electric current to a greater or lesser extent. We call this electrical resistance, or R. Resistance is measured in ohms. Its symbol is the Greek letter omega. Increasing resistance decreases the current flowing out of the battery in a circuit. Increasing voltage increases the current. Combine these two relationships and we get Ohm's law. So if you increase voltage, current will increase, but if you increase resistance, since it's in the denominator, the current will decrease. The units for current are amps, which can be seen to be volts per ohm by substituting into this expression. So voltage is in volts, resistance is in ohms, so 1 ampere is 1 volt per ohm. Be careful about applying Ohm's law. We'll use the water analogy again. Rocks in a river impede the flow of the water and reduce the amount of water flowing from its source. However, even if the water flow from the source is reduced, the amount of water that passes the rocks is the same as the amount of water that struck the rocks. The water leaving the rocks has less energy. Let's move back to electricity now. A greater electrical resistance in a circuit decreases the current leaving the battery. After it goes through a light bulb, the voltage decreases, but the current through the light bulb remains the same. All the charges that go into the light bulb leave the light bulb. So our little diagram down here, the voltage is decreasing. Here comes the current. The energy gets used up by the light bulb, and the voltage decreases until it comes back to the battery. However, the current is the same everywhere in the circuit. Ohm's law can also be rearranged to find the resistance if you're given voltage and current. R is V over I, or if we want to find the voltage giving the current through a resistance, V is I times R. And another video here on electricity. Some examples now. Calculate the electric current in a wire of resistance 4.5 ohms when the applied voltage is 18 volts. Our givens are voltage and resistance, so we use this form of Ohm's law, V over R, put in the variables, and we get 4.0 amps. How much voltage will produce a 0.30 amp current through a wire of resistance equal to 120 ohms? Well, this time we have current and resistance. So we take our version of Ohm's law here, solve that for V by multiplying both sides by R, and we get this. Substitute in our numbers, and we get 36 volts. What is the resistance of a coil of wire when 12 volts is applied and 0.040 amps of current flows through the coil? This time we have current and voltage, and we need to find resistance. So we start here, multiply both sides by R, and then divide both sides by I, and we get resistance is voltage over current, substitute in our variables, and we get 300 ohms.